Can humanity rebuild the magnetic field of Mars? In 2017, scientists proposed placing an artificial magnetic dipole at the Lagrange L1 point. Models show this could restore Martian atmospheric pressure to levels allowing liquid water to exist within centuries. On August 7, 1996, NASA held a press conference announcing they had found evidence of past life in a meteorite from Mars. That meteorite had slumbered in the Antarctic ice sheet for 13,000 years under the designation ALH 84001. But behind this discovery lay a more unsettling question. If Mars once hosted life, how did they die? The answers point in a single direction. The disappearance of the Martian magnetic field 4 billion years ago might be the culprit behind the largest known mass extinction event in the solar system. Tonight, let this question carry you slowly into sleep. 4 billion years ago, life on a planet was dying. And what killed them is something you cannot feel right now, yet it penetrates your body every second. Before reaching the hands of scientists, this meteorite traveled a journey 10,000 times longer than the entire history of human civilization. It formed on Mars 4.5 billion years ago, when Earth itself had not yet fully cooled. One day an asteroid struck Mars. The energy of the impact ejected a batch of rock fragments beyond Martian gravity. One piece began drifting in space. It drifted for 16 million years with no destination and no direction. Until 13,000 years ago, it entered the Earth atmosphere and landed on the Antarctic ice sheet. It was buried by snow, and then nothing happened. In 1984, an American Antarctic expedition found it near Allen Hills. They cataloged it, put it in a bag, brought it back to Houston, and placed it in a storage facility. It sat there piled up with thousands of other meteorites. No one thought it was anything special. It stayed in that warehouse for another 12 years. Until 1996, NASA geologist David McKay placed it under an electron microscope and saw something that made his hands tremble. It was a batch of nanoscale magnetite crystals. A single crystal measured about 50 nanometers in size, which is 1,000 times smaller than a human red blood cell and 2,000 times smaller than the diameter of a human hair. This size itself is not unusual. What was strange was their pure, flawless morphology and their neat chain arrangement. McKay's team scoured all known mineralogical literature. On Earth, only one thing can produce these three characteristics simultaneously, and that is magnetotactic bacteria. These bacteria synthesize magnetite crystals inside their bodies to sense the direction of Earth's magnetic field. And the morphology of the crystals they produce is almost identical to those in ALH 84001. McKay wrote up this discovery as a paper and submitted it to the journal Science. At the press conference, NASA Administrator Daniel Goldin said a quote that would be repeatedly cited. He said, "We have not found life, but we have found the suggestion that life once existed." Bill Clinton walked out onto the White House lawn and spoke into the microphone, saying, "If this discovery is confirmed, it will be one of the most significant scientific discoveries in human history." The front pages of major newspapers globally printed the photo of the exact same rock on the same day. That was the closest public moment in human history to confirming extraterrestrial life. Then, within 72 hours, dissenting voices began to emerge. The first wave of refutation came from mineralogists. They argued those magnetite crystals could also be generated by pure chemical reactions without any biological involvement. The second wave came from organic chemists. They stated the polycyclic aromatic hydrocarbons detected in the meteorite could be terrestrial contaminants rather than remnants of Martian life. The third wave came from biologists. They pointed out that the structures resembling microfossils were too small. They were 10 times smaller than the smallest known unit of life. That volume simply could not house the basic molecules required to sustain life. Despite this, McKay's team did not retract the paper. For the next 20 years, at every academic conference, they had to defend this rock all over again. This was not a victory, but a defense with no end in sight. Yet, this defense itself pushed a much deeper question to the forefront. Who exactly made those magnetite crystals? Over the next 30 years, this question split the world's top planetary scientists into two camps, and neither side has been utterly defeated. The core argument for the camp supporting biological origins is the simultaneous presence of those three traits, namely pure morphology, flawless structure, and chain arrangement. For the magnetite crystals produced by magnetotactic bacteria on Earth, these three traits are indispensable. This is because they are the result of bacteria precisely controlling the biomineralization process. Pure chemical reactions usually only meet one or two of these criteria and rarely achieve all three simultaneously. In 2001, the opposing side played their strongest card. A laboratory at the Johnson Space Center used the thermal decomposition of carbonates at 470 degrees Celsius to synthesize magnetite crystals of almost identical morphology. The entire process involved absolutely no life. After this experiment was published, the morale of the opposing camp surged. The supporting camp immediately fired back. They argued that in an environment of 470 degrees Celsius, organic matter would have burned away long ago. How could one explain the polycyclic aromatic hydrocarbons that coexisted in the meteorite? If it was a high-temperature chemical reaction, organic matter and magnetite crystals could not have been preserved together. In 2009, a Stanford University team reanalyzed ALH 84001 using a higher resolution electron microscope and found organic film residues between the chain-arranged crystals. This detail is crucial because no one has ever observed such an organic film in magnetite crystals of purely chemical origin. The supporting camp believed this was the trace left after bacterial cell walls degraded. The opposing camp argued that the film might be contamination from terrestrial microbes. This is the fundamental reason why this debate can never end. ALH 84001 was exposed in the Antarctic ice sheet for 13,000 years. Earth's water, air, and microbes all had the opportunity to infiltrate it. The possibility of any terrestrial contamination can never be entirely ruled out. This is an inherent flaw of this meteorite as evidence. It is not an issue with analytical technology, but a problem determined by its origin. David McKay passed away in 2013. Until his death, he firmly believed those crystals were evidence of life. This debate did not end with his departure. It became the most important case study in the history of science on how to define the standards of evidence for extraterrestrial life. It was written into textbooks and repeatedly discussed by every generation of planetary science students. But there is one thing that neither side of the debate disagrees on. Regardless of who made the crystals in ALH 84001, Mars once had an environment suitable for life. This point has been confirmed by geological evidence from subsequent space probes. And the end of that environment has a precise time node, which is 4 billion years ago. The appearance of this number is very subtle because on Earth's side another event occurred at that exact same time node. Greenland hosts a batch of ancient metamorphic rocks containing the oldest known evidence of life on Earth, which is an anomalous distribution of carbon isotopes. The time frame is roughly 3.8 to 4 billion years ago. The implication of this signal is that life on Earth was already conducting carbon metabolism at that time. Placing both events on the same timeline reveals that the Martian magnetic field began to rapidly decay about 4 billion years ago, while the oldest evidence of life on Earth dates back to roughly 3.8 to 4 billion years ago. These two events happened almost simultaneously on the cosmic clock, with a margin of error of no more than 200 million years. On a cosmic scale, 200 million years is a very small number. This means that at the exact moment life on Earth was born, Martian life might have been undergoing extinction. The same sun illuminated two vastly different destinies. The disappearance of the Martian magnetic field was not a slow, gradual process. Geological evidence shows that within a relatively brief time window of perhaps less than 500 million years, it plummeted from several times the strength of Earth's magnetic field to near zero. For life, this is equivalent to a protective shield being suddenly withdrawn. It did not slowly thin out, but rather one day it was simply gone. Why did the magnetic field of Mars disappear while Earth's did not? The answer lies in the volume difference between the two planets. Earth's liquid iron core is still rotating today. The electrical currents generated by convection drive the continuous regeneration of the magnetic field. This dynamo has been running for over 4 billion years and is still running today. The volume of Mars is only 15% of Earth's. Its core is smaller, and it dissipates heat much faster. Around 4 billion years ago, its core completely solidified. The dynamo stopped turning, and the magnetic field extinguished accordingly. The difference in volume determined the vastly different life and death outcomes of the two planets. What happened after the magnetic field disappeared? NASA's MAVEN spacecraft has measured the current atmospheric loss rate of Mars from orbit. The result is about 100 grams per second. It does not sound like much, but this is under today's relatively calm solar activity conditions. When protected by a magnetic field, this number is close to zero. The accumulation over 4 billion years is enough to evaporate a global ocean tens of meters deep. The oceans of Mars were blown away by the solar wind bit by bit, just like this. However, the disappearance of an ocean is a slow process that takes hundreds of millions of years. Before that, an even faster killer had already arrived. The strength of Earth's magnetic field is approximately between 25 and 65 microteslas. This strength can deflect cosmic ray particles with energies up to billions of electron volts. It pushes them away, forcing them to travel around the Earth. When a magnetic field strength drops below 10% of Earth's limit, the penetration depth of high-energy protons will increase from a few centimeters in the surface soil to several meters. This means that even underground shelters are no longer safe. Life has nowhere to hide. The Halloween solar storm of 2003 was the strongest solar particle event in recent decades. During that storm, astronauts on the International Space Station received a radiation dose in less than a day equivalent to the total amount a normal person receives in an entire year. Earth's magnetic field compressed the ground impact of this event to a negligible level. Most people had no idea what happened that day. But for Mars, without magnetic protection, every solar storm is dozens of times this intensity, striking directly without any buffer. A model published in the journal Astrobiology in 2020 provided a specific critical threshold. When a planetary magnetic field strength falls below approximately 15% of Earth's limit, the combined radiation dose of surface ultraviolet rays and high-energy particles will exceed the survival limit of the most radiation-resistant organisms known. This most resilient organism is called Deinococcus radiodurans. It can withstand a radiation dose of 15,000 grays, which is thousands of times the lethal dose for humans. It is known as the most tenacious life form on Earth. But this model suggests that even it could not hold on. Theoretically, radiation intensity decays exponentially with depth. At 3 to 5 meters underground on Mars, the radiation dose might drop to a level that allows microbes to survive. This is also why scientists believe that if Mars still hosts life today, it must be underground rather than on the surface. The surface is already a radiation desert. But the underground is only a temporary respite. Life was not instantly killed by radiation, but its population size was gradually reduced by radiation over millions of years. DNA repair mechanisms were continuously overwhelmed until they could no longer maintain a sufficient reproduction rate. This was a chronic silent extinction measured in geological time. There were no explosions and no dramatic moments. It was simply a matter of each generation becoming smaller than the last until one particular generation became the final one. While this process was unfolding, the surface of Mars was experiencing another kind of transformation. Before its magnetic field vanished, Mars was a planet remarkably similar to early Earth in a sensory way. The atmospheric pressure was about 1.5 times that of Earth today. Liquid water covered the northern hemisphere lowlands, and the sky appeared blue due to atmospheric scattering. Ocean waves crashed against basaltic coastlines, and water temperatures near the equator could reach over 20 degrees Celsius. If you stood on that shore and closed your eyes, the sounds you would hear would not differ much from those on an Earth beach. After the magnetic field began to decay, the first thing to change was not the disappearance of the oceans, but the auroras. When the magnetic field lost its constraint over solar wind particles, those particles could enter the atmosphere along any path. The entire night sky would ignite as auroras were no longer confined to the poles. This was a beautiful yet deadly signal. It meant the protective shield had started to leak. As atmospheric pressure dropped, the boiling point decreased, causing oceans to begin evaporating at lower temperatures. Temperature gradients intensified, and winds became increasingly violent. The color of the sky gradually shifted from blue to pink, and then to an ochre red, because the proportion of suspended dust in the atmosphere grew higher, while the gaseous molecules that scattered blue light became fewer. This color change did not happen suddenly, but took hundreds of millions of years. Every generation of life living there could not see any difference in the sky, but it was constantly changing. Scientists estimate that the last liquid water on Mars disappeared about 3.5 billion years ago. Before it vanished, the water had retreated into isolated pools at the bottom of impact craters. The salinity was incredibly high, and the pH levels were extreme, much like the most severe salt lakes on Earth, but even more isolated and hopeless. That was the last possible refuge for life. They were isolated puddles separated from each other by hundreds of kilometers of arid desert. Today, the average temperature on the Martian surface is minus 60 degrees Celsius, and the atmospheric pressure is only 0.6% of Earth's. If you stood there and took off your helmet, you would not feel the wind because the air is too thin to transfer any pressure you could perceive. 4 billion years ago, the sound of that ocean disappeared forever. But how exactly did the death of Mars occur? Did the radiation arrive first, or did the drought arrive first? The scientific community has debated this question for years, and there is still no definitive conclusion. The radiation fatality camp believes that after the magnetic field disappeared, solar wind directly bombarded the surface. Within millions of years, the radiation dose exceeded the survival threshold for life-leaving organisms with no time to adapt. The ocean evaporation camp argues that the drop in atmospheric pressure and the disappearance of the oceans were the more fundamental killers. Life might have persevered in an environment with enhanced radiation for hundreds of millions of years until the very last drop of liquid water vanished. Evidence supporting the radiation first theory comes from the mineral oxidation signatures in Martian meteorites. These show that the Martian surface underwent a dramatic oxidation event about 4 billion years ago, which is consistent with the chemical effects produced by solar wind particle bombardment. Data from the MAVEN spacecraft also indicate that during periods of active solar youth, the atmospheric escape rate could be 10 to 20 times higher than usual. This means that in the era when the young sun was far more violent, the speed of atmospheric loss was much faster than it is today. Evidence supporting the ocean evaporation first theory comes from geological river delta mineral deposits on Mars. The geological features left by this liquid water persisted for a considerable amount of time after the magnetic field disappeared, indicating that the atmosphere did not collapse immediately. The groundwater system might have been sustained for hundreds of millions of years after the surface oceans vanished, providing a final sanctuary for subterranean life. Both hypotheses share a common blind spot. We do not know the upper limit of radiation resistance for Martian life if it existed, nor do we know whether they possessed a fast enough evolutionary rate to migrate underground when the pressure increased. These two unknown variables leave the conclusions of any computer model suspended in midair, unable to land on a solid answer. The true significance of this debate is far greater than it appears on the surface. If radiation is the primary cause, then any planet without a magnetic field cannot sustain surface life long-term, meaning the number of habitable planets in the universe would drastically shrink. If ocean evaporation is the primary cause, then the magnetic field is just one of many influencing factors. The resilience of life might be much stronger than we imagine, allowing it to hold out much longer, even under harsher conditions. The two answers point to completely different cosmic landscapes, and we still do not know which one is true. To find out which is true, we need better evidence. But this is exactly where the scientific community is stuck. The reason we are stuck is not that our space probes are not advanced enough, but something much more fundamental. the scientific community has yet to reach a unified standard on biosignatures for life. Methane can be produced biologically or geologically. Organics can be remnants of life or brought in by meteorites. Even oxygen under certain planetary chemical conditions can be generated non-biologically. Every single piece of candid evidence has a non-biological explanation. Not one is an ironclad proof that only life could leave behind. The Curiosity rover discovered organic molecules and seasonal methane fluctuations in the Gale crater. This discovery was exciting enough, but it could not differentiate between biological and non-biological origins. The Raman spectrometer carried by the Perseverance rover can detect organic molecules, but its resolution is still insufficient to identify attributes unique to life. The amino acids manufactured by life are almost exclusively left-handed, whereas pure chemical synthesis produces an equal mix of left and right-handed molecules. This chirality difference is one of the most reliable indicators to distinguish biological from non-biological origins. However, current instruments on Mars simply cannot achieve this level of precision. The only truly viable way to solve this problem is to bring Martian rocks back to Earth and analyze them using the most advanced laboratory equipment on our planet. The Perseverance rover has already sealed 43 rock core samples, neatly placing them on the Martian surface waiting to be retrieved. The mission to fetch them is scheduled for the 2030s, but the budget has inflated from an initial estimate of $4 billion to over $10 billion, putting it at risk of being canceled. Even if the sample return mission is successfully executed, there is another dilemma. If we bring Martian samples back to Earth, we must ensure we do not contaminate the Earth's ecosystem. Just in case Mars actually has living microbes, we cannot let them escape. At the same time, we must ensure that Earth microbes do not contaminate the samples. Otherwise, the analysis results will be invalid. Satisfying both requirements simultaneously demands quarantine facilities that humanity has never built before. The cost and complexity alone present a massive engineering challenge. The quest to find Martian life is essentially an experiment that can only be conducted once. We only have one Mars. Every exploration alters its state, and every probe we send could be the next source of contamination. This is not a technical issue, but rather a reality dictated by the very nature of the question itself. Faced with these difficulties, there is a question worth pondering. What would Mars look like today if its magnetic field had never disappeared? Let us assume Martian core did not solidify 4 billion years ago, and the liquid iron core continued its convection, maintaining a magnetic field at over 50% of Earth's threshold. What kind of chain reaction would this single variable change trigger? The first step is atmospheric retention. MAVEN data shows that under magnetic protection, the atmospheric escape rate is close to zero. 4 billion years later, the Martian atmospheric pressure might have been maintained at 0.5 to 1 Earth atmosphere, which is enough to allow liquid water to exist stably. The greenhouse effect would maintain surface temperatures within the range for liquid water. The second step is the evolutionary timeline of life. It took Earth life about 3 billion years to evolve from single-celled to multicellular organisms, and another 600 million years to go from multicellular to complex animals. If Martian life had not been interrupted 4 billion years ago, they would have had 4 billion years of evolutionary time by today, possessing an evolutionary window almost identical to that of Earth life. The third step is the possibility of civilization. Mars has a smaller mass. Its gravity is only 38% of Earth's, and its escape velocity is only 5 kilometers per second, compared to Earth's 11.2 kilometers per second. A Martian civilization at a similar technological level would find the threshold for developing rocket technology far lower than on Earth, making space entry vastly easier. The fourth step envisions a solar system with 2 civilized planets. At their closest, the 2 planets with intelligent life would be separated by only 55 million kilometers, which is roughly 140 times the distance from the Earth to the Moon. On a cosmic scale, this is practically right next door. Would such a solar system be an Eden of cooperation or a competitive battleground? Nobody knows. This chain of deduction could break at the very first step. Because Mars has a small volume, even with a magnetic field, its volcanic activity would stop much earlier. The carbon cycle might fail to be maintained, and the atmosphere would still be gradually lost. Whether life would inevitably appear, and whether it would inevitably evolve into complexity, are all unknown variables. But the value of this deduction does not lie in the answer. Rather, it helps us clearly see just how many cosmic coincidences the existence of Earth today relies upon. 4 billion years ago, the magnetic field of a planet extinguished. Its oceans slowly evaporated over hundreds of millions of years, and its sky turned from blue to ochre red. Its life, if it ever existed, dwindled generation by generation under the dual oppression of radiation and drought. It continued until the very last one vanished in a hypersaline puddle at the bottom of an impact crater, leaving no trace that we can confirm. And at that exact same moment, 150 million kilometers away, the liquid iron core of another planet was still spinning. Its magnetic field was still there. Its oceans were still there. Its life was just beginning. That planet is Earth. Those newly begun life forms spent 4 billion years transforming into you. The bed you are lying on right now is well within the protective embrace of Earth's magnetic field. Out of all the cosmic rays passing through your body at this very moment, only a tiny fraction of particles with high enough energy can reach the ground, and the vast majority of them pass right through your cells without altering a single thing. Your DNA remains intact tonight, and you will still be you when you wake up tomorrow. This is not something to be taken for granted. This is because 4 billion years ago, a planetary core happened to be just large enough. It happened to cool slowly enough. It happened to maintain a magnetic field, and it happened to give life the time to evolve into you. All these coincidences perfectly stacked together to create the you who is listening to this audio right now. The fact that you are alive is something far more rare than you might think. The story of Mars is not over yet. Those 43 rock core samples, sealed by the Perseverance rover, are sitting on the Martian surface, waiting for the day they are brought back to Earth. Perhaps on that day we will find a trace within a red rock that only life could have left behind. Perhaps we will not. But no matter what the answer is, one thing is already certain. Thousands of kilometers above your head, right now there is something you have never seen and can never thank. Every single second, it is blocking the solar storms for you. It does not need you to know of its existence, nor does it need your gratitude. It is just there. It has always been there, and it has been there for 4 billion years. Looking back at the tragic fate of Mars, we realize something profoundly beautiful about our own existence. We often get caught up in the heavy pressures of daily life, like the bills, the deadlines, and the endless anxieties. But when you zoom out to a cosmic scale, just the simple act of taking a breath is a staggering miracle. For 4 billion years, an invisible magnetic shield has tirelessly defended us against the brutal fury of the universe, allowing a chain of life to remain unbroken until it finally reached you today. The greatest lesson Mars teaches us is not just a story about planetary death. It is a profound reminder to cherish our fragile and beautiful Earth, and to be deeply grateful for the incredibly rare privilege of being alive. Every ordinary moment you experience is the result of billions of years of cosmic luck. But of course, the universe holds endless mysteries, and science is an ongoing journey of seeking the truth. Everything I just shared in today's video is based on my personal perspective, synthesis, and analysis. It might be entirely right, or new discoveries tomorrow might prove me completely wrong. That is exactly the beauty of science. So, I want to pass the question over to you. What do you guys think about this story? Do you believe the death of Mars happened exactly like this, or is it just a wild theory? Is the evidence compelling enough for you? I would absolutely love to hear your thoughts so we can explore and debate this together. Also, the universe is vast, but the internet connects us all. Where exactly in the world are you watching this video from right now? Please drop your city or country down below and let me know. Thank you for journeying with TIAN Science today. I will be reading and liking your comments, so I will see you all down in the comment section. Stay curious and see you next time.